Okay, so welcome back to class. The plan for today is really just to cover one topic, related rates, section 3.9. Um, if we get through 3.9 a little early, I don't want to start 3.10 today. I know it's kind of ironic that it's a math textbook and there's a 3.10, but it comes after 3.9, but it is what it is. Because linear approximations and differentials is, I think probably if you had to pick maybe three most important topics from Calc 1, it's probably in the top three. So I want to make sure that we give that kind of a full treatment on its own, and that the kind of beginning where we lay out kind of the thrust of that material is connected to the actual practical computation of linear approximations and differentials and all of that. So um, the goal today is really just to get through related rates. Couple other administrative notes. We've got a couple administrative things to handle today. The first is that midterm course grades will be posted this week. Unfortunately, midterm course grades for the classes where I have one midterm exam, one final exam, tend to come before, or will always come before the midterm exam is taken. So students often are confused. They're like, wait, how did I get a midterm course grade? We didn't take the midterm exam yet. Did I like miss the midterm exam? No, they're two separate things. So the midterm exam is just the exam that's in the middle of the term as opposed to the final exam that's at the end of the term. The midterm course grade is just an estimate of your current standing, your current grade in the course at the time that grade is computed. So it is the midterm course grade because it is also in the middle of the term. So they're named similarly, just like the final course grade is at the end of the term, but it's not just like the final exam grade. So first note on that, you're going to see a midterm course grade. It doesn't mean you missed the midterm exam. That midterm course grade will basically just be your homework average for the homework sets that were due, well, I suppose due yesterday or before. So when I compute it, I'm just going to use homework because we don't have exam information yet. Uh, and in general, in midterm course grades, I mean, this is certainly true for my courses, whether we're in a course where, we have a midterm and final structure where we don't have exam information yet, or whether we have a couple of exams and maybe we've taken, say, a unit exam or so at this point, and there is a bit of exam information. So whether it's my courses or I think this same idea applies, I would think, across the board to everybody's courses. Uh, a midterm course grade comes with a lot of caveats. If you think that you're doing well in the course, if you think that you're sitting at like if you're doing A, B work and you get a midterm course grade of F, there's a disconnect there somewhere. Check in with your instructor. Um, is there a reason for that? Did you like miss an exam? Are you just, did you get 50% on a whole bunch of homeworks and kind of, not do that great on those homeworks or something? Is there a reason for that? Did your instructor compute it incorrectly or something? It's a good thing to reach out in that case, or vice versa. If you think you're doing horribly in a course and you see that your midterm course grade is A or B, again, your expectations might be a little different than at least what the instructor's perspective is. Um, if you feel like you're doing B work and you see a midterm course grade of C, or you feel like you're doing B work and you see a midterm course grade of A, it's not really that granular or accurate. One of the issues with midterm course grades is it's supposed to be an estimate of your current standing in the course, but that's not really a well-defined statement, right? So really what it's supposed to say is something like, if you continue working in the second half of the course the same way that you worked in the first half of the course, what could you reasonably expect your final course grade to be? Um, but in reality, there are so many assumptions that have to go into such an answer that it's that's not an easy question to answer. Um, so I wouldn't look at midterm course grades, as like a B is all that much different than an A or different than a C, but like, almost like a pass fail kind of thing. Like if you think you're doing well and you see a D or F, or if you think you're doing terribly and you see an A or B, maybe, uh, maybe realign your expectations or figure out what the cause of that disparity is. Um, So that's how I would treat midterm course grades. And like I said, the way that I'll compute them, practically speaking for you, will just be the average of the homework sets that were due yesterday, so 10/6 or earlier. Um, I think there was one other. Oh yeah, if you want something that's a little more accurate to your situation, something that is good and something that I used to do uh, for some courses was just make an Excel spreadsheet and have, homework grade, exam grade, and so on, the way the final course grade is computed. And as I would go through the course, I would update that information and I would do scenario analysis. So I would say, okay, up to this point, I've got a 87% on the homework. Do I think that I can continue putting in the same level of effort? And do I think that the difficulty of the material is not going to ramp up significantly? In this course, it probably won't. In a course like, say, Math 90, it does ramp up significantly. The first half is much easier than the second half for most students. But in this course, probably about constant difficulty most of the way through. Um, so okay, I can continue putting in this effort. I look, in the next couple months, I don't have anything that would make my effort have to decrease or so okay, if I keep my homework the same, if I were to get this grade on, the midterm exam, this grade on the final exam, what would my final course grade look like? Or maybe, a couple weeks from now, we have the midterm exam uh, information back. So you've taken the midterm exam, you know what that number is. Now that number is set in stone. You put that in there. Okay, now what does the balance between homework and final exam look like? If I want to get a B in the course and that would require me getting a 96% on the final exam, I probably want to take a bit of weight off the final exam. So I want to maybe boost my homework score over the next month or so. Maybe I'll plan to put a little more effort into my homework score for this course, or maybe I'll choose to settle for, a lower grade than will be optimal, something like that. So I think doing your own scenario analysis where you kind of understand all of the variables at play, you understand what other courses you have and other life responsibilities you have, and how much flexibility there is. I think that's a good thing to do. So that's my spiel on midterm course grades. Like I said, it definitely applies to my courses, and I think this actually applies more generally, probably to all your courses. So this is something you know, I don't think it would be a bad idea to apply to any course that you're, kind of concerned about your grade in. Not concerned as in a bad thing, but any course that you say, I really want to target, this grade or higher in this course. Um, okay, so any questions on midterm course grades? But big thing, you're going to get the most important thing is you're going to get a midterm course grade pop up on your portal this week, and it doesn't mean you missed the midterm exam or something like that. Two different things. And then last administrative detail for today. So I met with our Proctor U, point person at CCAC, and we talked over some of these tech issues, and we don't have an answer yet, and it doesn't look like we're going to get an answer quickly. Um, so, long story short, Proctor U doesn't work all that well with WebAssign, and we think we have some workarounds, but we want to test them first, and it's going to take a bit of time. So, however, we have actually got Examity through the end of this semester. So we're switching over to Proctor U. The switch was supposed to take place this semester, but they kept Examity live for us because of these Proctor U challenges we're having. So we'll be using the Examity proctoring system. If you've used it before, it's the one that we've used for the past few years at CCAC. And I use the automated setting on the system, so it rarely has any tech issues. When you do the live proctoring, there's just a lot more, pieces that have to fit into place just right, like your Zoom session and the proctor Zoom session, not their internal version of Zoom. It's not really Zoom. They have to both work. The proctors, internet connection has to be stable enough, which a lot of times they're not in the US and their internet connections aren't super stable. So that causes some hassle. There are sometimes language barriers with the proctors, so they interpret exam instructions incorrectly. None of that, you don't have to worry about any of that in this course. I just use the automated setting. So you just log on, you start the system up. it starts, the camera and the screen recording. You take the exam, you submit the exam, log out of everything, and you're done. Uh, to that end, because, even with the simpler process, it still is a non-trivially complex process. Um, I'll post an Examity practice exam. I'm probably going to try to get that posted today, but by tomorrow at the latest. And the only purpose of this Examity practice exam, I'll also send in an announcement out with this information in it as well on Blackboard and copied to your emails. But the only purpose of this Examity practice exam I'm going to post is for you to practice the process of logging onto Examity. So to log on, get your credentials all set up, and to, kind of start up a testing environment. There's the Examity practice exam on WebAssign. We'll have like, I think it's 5 basically dummy questions. I mean, just kind of 5 random questions that, some of them are text box and things that you can type in and just make sure that all the tech is working. This doesn't count towards your grade, and it's not meant to be an assessment of how well you know the material, or it's not meant to be uh, an academic assessment. It's really just for you to practice the tech and make sure all the tech is working right, that you got the Examity account set up and everything before it comes time for the actual midterm exam. So keep an eye out for that exam to be posted and for the announcement to come out. I posted it for one of my courses over the weekend, and I just checked just before we started class, and nobody has completed it yet. So I'm crossing my fingers. I would like somebody from that course to actually complete the Examity practice exam so that I know for sure that everything's working and that, nothing's wonky, and then I'll kind of roll it out to all my courses. But definitely it'll be available by tomorrow, whether or not my other course, somebody successfully completes it. I think it should work, but I just want to make sure, because we were going to switch to ProctorU, and, now Examity is live, and I just want to just make sure everything's working. Better to roll out to 1 class if there's an issue than to have it rolled out to 5 classes. But so anywhere that you see mention of ProctorU in the syllabus or anything like that, we're going to be using Examity this semester instead of ProctorU, which I think is a huge plus. The Examity system is just better in general than ProctorU, regardless of the tech challenges with ProctorU. So keep an eye out for that. The announcement will have a lot more information on that. And we have the midterm exam coming up in a couple of weeks. So we will use Examity for that midterm exam. So I would strongly recommend completing the Examity practice exam this week if you're able to, just to give yourself the maximum amount of time that if there is any tech issue, I don't think there should be any on like CCAC's or Examity's side. Things should be working. But, if you have a browser issue, or if your computer is not working nicely with it, or, you need to get a webcam or something like that, you want to give yourself a good buffer to get that all sorted out before the midterm exam week. So that's really the point of this, is to make sure all the tech is working. Any questions about any of that? I know that was kind of a lot of administrative stuff all at once. Questions on anything? Okay, and then our quote of the day today is sometimes just quoted as the words B1 by Marcus Aurelius, the Roman emperor. But that also kind of sounds like B1, like, be one with the world and Zen and all of that. And really what this comes from is a quote roughly translated as, stop arguing about what it means to be a good man, be one, or a good person, be one. So, Marcus Aurelius was an emperor, but also kind of a philosopher. He wrote a book, Meditations, actually wrote it in Greek, even though he was a Roman emperor. My argument would be that because Greek is a better language, although that's a never-ending argument in classics department over whether the Greeks are cooler or the Romans are cooler, or whether the Greek language or Latin language is the cooler language. But anyway, so I think it's easy to kind of sit around a table and argue and debate about things, and from the kind of the comfort of our home, so to speak, whether literally or metaphorically, and never actually go out and implement those practices. And that's what he's getting at here. He's saying, okay, like, you know, if you get to 99% understanding of what it means to be a good person as opposed to 95% understanding, but you never actually do anything, then you have like 99 times zero versus like 95 times, a lot is a lot more than zero. So, don't plan too much, too extensively. At some point, you have to implement. Um, okay, so that is our lead up to today. And moving on to now related rates. So we're going to see that we talked about implicit differentiation before. We're going to see that related rates is kind of a closely related idea to implicit differentiation. Okay, so let's look at this motivating example. We're going to jump right into an example and try to build out some aspects of related rates with this example. Then we'll look at the procedure and then we'll solve a couple of more challenging examples. So let's consider a rectangle. It has a length and a width, but its length and width are changing over time. Its length is increasing at 3 inches per second, and its width is decreasing at 2 inches per second. So let's say we have a rectangle, and we'll call this direction width and this direction length. And we want to know, for instance, maybe how its area is changing when the length is 12 and the width is 5. Or maybe at a different point when the length is 6 and the width is 9. So if we think of an axis in time here, well, so what is this rectangle going to look like at different snapshots in time? At some point, we're going to have a length of 12 and a width of 5. The length is increasing and the width is decreasing. So let me maybe write that, say, here. At a different point, we might have had a smaller length and a wider width. And we could imagine that over time, if we took snapshots at different points of time of this rectangle, at some point it would have been really wide and short, maybe a little, I can't quite squeeze it in here, but a little less wide and a little taller. A little less wide still, if you kind of imagine, it's kind of squeezing one in there. A little less wide still, a little taller still. Maybe here it would look almost like a square, a little less wide, even taller. And then over here, it's quite tall and really skinny. So as time evolves, we go from this kind of wide and flat rectangle, and it gets taller and skinnier as time progresses. So if we took some snapshots of it over different times, we might see something like this. We can also imagine that in each of these snapshots, there's an area. And this area is going to be a function of time. Right? The area is the thing that we're asking about. And in fact, if I graphed area as a function of t, I see that way off to the left, I mean, I have in the extreme a rectangle that's pretty wide but has 0 height. Well, that's 0 area at some, let's not make it at 0 at some initial time, there's 0 area. And then if I let time go too far, then I have a rectangle that's kind of tall but has 0 width. So it has 0 area as well. And in the middle, I have some rectangles with positive area. So how is the area changing? What's the rate of change of the area when, say, maybe this is time t1 and this is time t2. Maybe this is t1 and t2 here. I don't know when these times are, so don't, this is just a schematic. Don't tie yourself too deeply to whether the slopes are positive or negative or 0 or anything. We're just making kind of a schematic here. Right. So I could think of the slopes of these tangent lines, dA by dt, and I see that dA dt is going to change uh, over time. So whether I take the snapshot here or there or somewhere else, my instantaneous rate of change of that area, at least seemingly, is going to be different uh, at different points in time. I also know that my area is related to length and width, of course, right? The area is length times width. And the dependence on t comes from the fact that the length is really a function of t, right? Oops, the length is increasing over time. And the width also is a function of t. The width is decreasing over time. We actually don't really have a good handle on whether we expect the area at either of these points in time we're interested in to be increasing or decreasing. One of my inputs is increasing, one of them is decreasing. They both have kind of a positive relationship with my area. You know, if the length gets bigger, area gets bigger, all else equal, and similarly for the width. So they have kind of countervailing impacts, right? uh, the length is tending to want to make the area bigger over time, and the width is tending to want to make it smaller over time. Who wins out at what points in time is going to be a matter for the details. So I actually don't have a really good, I don't have a really good intuitive um, feel for like whether dAdt should be positive or negative or zero at different points, or but I do know that it does seem like it should change over time, because I got to be zero at one point, zero at another point, and I've got to connect the two with a continuous function um, that's always non-negative. I mean, it seems like I probably am going to come up, hit a zero derivative, and then come down. Okay, so I've related the quantities in question. I want dAdt. And I, of course, suspect that dAdt is going to probably depend on dLdt and dWdt, where dLdt is, well, that's this rate of increase of the length, this plus 3. And dWdt, the width is decreasing at 2 inches per second. Everything is in inches and inches per second and so on. I suppose I probably should have said like inches and all of that here, but so all of these L's and W's are in inches. Yeah, this isn't physics class. This is a chemistry class. We avoid units when possible, and we have to deal with units. We make it easy. Um, so everything's in inches and seconds and all that good stuff. So dWdt is going to be -2. And this is where we get the term related rates. I want to relate the rate dAdt that I want to know something about to the rates that I do know something about, dLdt and dWdt. If I want to relate dAdt to dLdt and dWdt, it helps an awful lot if I related the underlying quantities first, A, L, and W. And I do have that. So I know how A relates to L and W. A is L times W. Now I want to take that and I want to relate dAdt to dLdt and dWdt, and I do that by taking the derivative with respect to t on both sides. This just feels like implicit differentiation, right? I just apply this d by dt operator to both sides of my equation. Everything here is a function of t. I'm not writing out all of the explicit dependencies on t, but A, L, and W all depend on t. So on the left side, I just have d by dt of A, or well, that's just dAdt, the thing that I'm interested in. On the right side, super tempting to just write dLdt times dWdt. Be really careful though. Product of two functions of t. We better use the product rule here. So dA dt is L times dW dt plus dL dt times W. Note that if we had made a mistake here, let me write this in red because it's a mistake. If I had made a mistake here and I had written dA dt is dL dt times dW dt, but dL dt and dW dt are always the same, right? Plus 3 inches per second minus 2 inches per second. The ADT is going to be 3 times -2, or -6. Well, -6 is our result. Well, I have two issues here. One issue is, well, my units here, let me switch away from red for units. My inches here are inches per second and inches per second. But the ADT is a rate of change of area with respect to time. This should be in square inches because area is measured in square inches per second. But I actually get square inches, that's okay, over square seconds. So actually my units don't mesh here. That might be the first indication or one indication that something's wrong. The other indication that something's wrong is that, well, dA dt is just a constant -6. It has no explicit dependence on t or implicit dependence on t through L and W. In other words, anywhere that I look through this like movie, you can think of it as playing here as the rectangle goes from being short and wide to tall and skinny. This movie, as it progresses along, wherever I take a snapshot, I'm claiming that dA dt would still be -6. But clearly that's not the case, right? The ADT is not just going to be negative everywhere. Our tangent lines aren't going to have negative slope everywhere. That clearly can't be true. We don't have to prove that mathematically. We just see that that doesn't mesh. So I'd say the very first thing is to get an understanding of the problem, an intuitive understanding. If you have units, as much as being a math guy, I don't like units. Sometimes they are quite helpful. If you get inconsistent units at the end of your problem, if you get a quote answer in terms of units that aren't what you should get, that might be an indication that something went wrong somewhere. And then also, here this just doesn't match the reasonability condition that, well, we said that we expected the ADT to be positive for a bit, 0 at one point, and then negative for a bit, based on our picture here. I mean, maybe our picture is more complicated. Maybe it does something like this, but we certainly don't expect it to just have a negative tangent line with slope -6, or a tangent line with slope -6 everywhere. We certainly don't expect that. So if we made that mistake and forgot to apply the product rule, if we keep perspective on the problem, well, we see that that couldn't be right. We rewind, we say, where did I go wrong? Oh, wait, that wasn't right. Let me do the product rule. Now here I do see an implicit dependence on time through the presence of L and W. When I have different values for L and W, I might be taking a snapshot here or there. I'm at a different point in this like movie, this progression of the change of this rectangle. So I do expect that my dA dt is going to change over time because of the presence of the L and the W here. Oh, trying to get those errors to go away. There we go. The second thing, if I look at my units, again, what do I expect for my units? Area is measured in square inches and time in seconds. So I expect rate of change of area per unit time to be like square inches per second. These units. are they equal to, well, what do I have over here? I have something that's like a length, units of inches times inches per second plus the same thing. And yeah, square inches per second, squares per second, this does make sense. So now after I carefully apply my product rule, I see my units come out right. And I do get, I mean, I don't know if it's going to look like this. Maybe I made a mistake somewhere else, but I do at least get an implicit dependence on time. My dAdt is going to change over time because L and W are changing over time. Okay, so at this point, I am pretty confident up to that step. And now I can answer my question. Well, my two questions. When length is 12 and width is 5, and when dLdt is +3 and dWdt is -2, what is the rate of change of the area? So what was, I said too many numbers all at once. L is 12, W is 5. Maybe I'll switch colors here. And dLdt is +3. dWdt is -2. Now I just plug these quantities into my model for dAdt here. So L is 12 times dWdt is -2 plus, well, I'll just do W is 5 times dLdt is 3. So I have -24 plus 15. And I think that gives me -9. And I probably ought to write inches squared per second. So I see my dAdt is negative at this point. I know with a length of 12 and a width of 5, that's kind of a tall and skinny rectangle, and it kind of seems like we should be kind of to the right side of things. This is sensible. It's reasonable, right? Um, that's not like a mathematical proof that, we've checked things and it's definitely right, but it's kind of in line with my gut feeling with my expectation. What about a different scenario when length is 6 and width is 9? So earlier in this process. So when length is 6, width is 9, and my dLdt, dWdt are still the same, 3 and -2. Then dAdt is L, or 6, dWdt times -2 plus W, 9 times dLdt, or +3. So we have 27 minus 12 is +15. +15 square inches per second. And again, we're looking at a triangle that's uh, kind of short and wide. We're looking at a rectangle that's short and wide. We're looking at one that's kind of maybe earlier on in the time frame. And that does kind of mesh with it having a positive slope from our picture here. Again, if we, this isn't a proof, this isn't, but it meshes with our gut feeling, it meshes with our expectations, makes us a little more confident that this is the right answer. So in application problems like this, setting up some reasonability conditions, what do I expect to get out of my problem? Maybe in terms of units, maybe in terms of just general structure. Do I expect the rate of change to be positive or negative? Do I expect it to be a big or a small number in magnitude? Um, uh, can I set up extremes? Can I say, okay, given the way this problem is set up, my, in a different context, the ADT can be no less than this number and no bigger than that number. Give me a bound to work with, right? So can I set up some boundaries on my problem, on my answer, where I get the answer and I check it against those conditions? And if it falls within those conditions, more satisfied. I haven't proven that it's the right one, it doesn't prove it. I could have still made a mistake. Um, but if it falls with outside of those boundaries, then I'm pretty confident something went wrong somewhere, and I better go back and check my work. Okay, so what is the kind of general process then? Well, step zero, before we even start into any of the details, the algebra, the calculus, any of that, we evaluate the problem statement. We determine which rates need to be related, right? What information is given to us, what information is asked for. And then we establish, again, what I call kind of reasonability conditions on the answer. Anything that we can glean from the problem and our understanding of it that's not calculation based, right? Like up here, I kind of imagined this movie progressing. I saw that I had zero area to the left and zero area to the right on the time axis. And I had positive area in the middle. I'm guessing that my area function looks something like this. And I can, you know, tell from that, for instance, that my dAdt is not going to be constant. I can expect it to be positive for earlier times and negative for later times, maybe zero, somewhere in the middle there. I don't know for sure that this is what the picture looks like, what the graph looks like, but seems pretty reasonable. After I do that, I look at the rates that I want to relate, and I relate the underlying variables algebraically. Now, this step one, I mean, it's, one step of three or four, whatever, however you want to count it. But this can be a really cumbersome step, right? Typically, step one isn't going to use calculus. This is going to use all of your geometry and trig and pre-calc and all of that knowledge from earlier courses. So often step one is, you know, uh, quite a tricky part of the process. Once we have the variables related algebraically, I mean, up here, it wasn't a tricky one. That's a pretty easy set of variables to relate, but not all problems are this simple. Once we have the underlying variables related, we differentiate to get related rates. So this is our calculus step. We want to differentiate carefully, be careful that we don't make silly mistakes like this. After we differentiate, it's a good thing to check, and when we differentiate, we change the units around a bit. So we probably should check again and make sure all the units, mesh correctly and everything, make sure that our derivative makes sense in the context. Very importantly, only after we differentiate do we plug in the constants. If I had tried to, so another thing that folks sometimes try to do is sometimes they try to plug in the constants too early. If I had tried to plug in 12 and 5 here, and then somehow get to dAdt, well, now I just get A is 60 square inches. I mean, okay, like that gives me the actual area at this point, but now I've kind of like set that in stone. I've removed all of the ability to change, to vary the input variable, because I've said like, okay, I took this one snapshot, this one frame, I sliced it out of the film, and I'm just looking at it. How is the area changing? Well, looking at that one frame, I can't tell. So we want to resist the temptation to plug in our numerical values too early. We make sure to relate our underlying variables for the rates that we want to relate. And then we differentiate. And only after we differentiate and we have our rates related, that's when we plug in the actual values. Now, there is maybe one or two caveats to that. Sometimes you can get away with plugging in a value a little bit early, particularly if it doesn't change as you're imagining this kind of movie, so to speak, progressing. If there's a value in there that doesn't change, that stays constant, well, then I guess you can plug it in. It's not going to hurt anything because it's staying constant anyway. But kind of as a kind of typically, we want to hold off on plugging in any values until after we've done the differentiation. So plug in constants, get the answer, and then once we get an answer, check that answer against our reasonability conditions. Max or min bounds on our answer, whether it should be positive or negative, um, whether the units match up, things like that. Okay, so let's apply this process then to an example here. So at noon, ship A is 90 kilometers west of ship B. Ship A is traveling south at 20 kilometers an hour. Ship B is traveling north at 10 kilometers an hour. And our question is, how fast is the distance between the ships changing at 4 p.m. the same day? And because we're good scientists, we will doubt all knowledge and assume the Earth is flat, so we don't have to deal with geometry on a sphere. Not even really a sphere anyway, right? So if you want to really frustrate somebody, uh, ask them to debate somebody on whether the Earth is flat or round, and then just ask them to define flat and round. And it's actually an incredibly difficult thing to define, right? Because you can take like a sphere of Play-Doh and smush it and make it flat. So they're kind of topologically pretty similar, and it's quite difficult to define flat versus round in a very precise way where you can argue something scientifically. Um, so if you want to frustrate, so that's always a good way to just like, you know, nuke a conversation with somebody if they're debating about something. Just ask them what they mean. Just say, you use this word. How are you using that word? What do you mean by that? What's your definition for that? And most people use most words um, without having precise definitions, and then argue on the basis of the meaning of that word. So um, semantics is important. Uh, Greek word semantikos means important. So the semantics, the meaning of words is quite important. So we will assume the Earth is flat um, because we can, I suppose, because it makes our lives easier. Okay, so what do I have? Ship A is 90 kilometers west of ship B. So here's ship A, and here's ship B. You can tell that I'm not an art teacher. Ship A is 90 kilometers west of ship B. Ship A is traveling south, and ship B is traveling north. Maybe I'll keep that. Maybe I'll keep that blue. And I see that there's a distance between the two ships at any given time. Okay, so maybe I will call the the distance that A has traveled south. Maybe I'll call that X. So that's this distance. And maybe I'll call the distance that ship B has traveled north Y at any given time. X and Y are functions of T. I'll call the distance between the two ships Z. I, I would love to call it D, but we already use D all the time for derivatives, so I don't want to be doing like dd by dt. That's just going to be really confusing, so we'll just call it Z. Now I have an east-west distance. If I imagine like playing this out in my mind, like what's going to happen with these two ships? They're going to start like this, and then they're going to, I don't know if this is the right way from your perspective or not, but I can never remember if Zoom like switches it around or what, but then they're going to start, one's going north, one's going south over time, right? So the movie is going to progress like that. This actually east-west distance isn't actually changing at all. There's nothing wrong with putting a variable in here, call it A or something like that. And say A equals A of t, but we notice that this distance, the east-west distance, is not changing at all, so dA dt is just 0. So I could actually just put in 90 here for my green distance, my east-west distance. I can put that in the beginning because as the movie progresses, these ships are getting farther apart, but they're never getting further apart in the east-west direction. It's only the north-south direction. So I see X and Y are in kilometers. X prime and Y prime are in kilometers per hour. And I see that Z is in kilometers. I want Z prime, which would be in kilometers per hour. The 90 is in kilometers. Okay, so let me think about this a little bit. I see that I have units that I desire. So I have kind of one reasonability condition. I know that X prime, the rate of change of this distance from ship A's initial point to where it is now, that distance, X prime is going to be positive, and Y prime is also going to be positive. So X prime and Y prime are positive. Well, Z prime is also going to be positive. The ships are getting farther apart over time because one's going south, one's going north. They're not moving east or west at all. If I imagine, if I imagine that the ships were, say, further apart east and west, if they were super far apart, you know, 1 million kilometers east and west apart, where we have a flat Earth and it's as far as far out as we want to go. If we were 1 million kilometers east west from one another, and then we went like, you know, whatever, 30 kilometers north and 60 kilometers south or something, we're still basically 1 million kilometers apart, right? So if we're really wide apart in the east-west direction, dz/dt is basically zero. So z prime is bigger than zero, but it's close to zero when far apart in the east-west direction. The other extreme is if we're really close together in the east direction, and in the most extreme case, if we start at the same point. Our ships start like back to back, you know, like they're doing a Hamilton style, you know, standoff or whatever they call it, you know, duel or something, and they start going in opposite directions. If my ships were back to back and going in opposite directions, then their speeds just add, right? No relativity here either, so making all kinds of simplifying assumptions like good scientists. But if the ships are back to back and they start just moving straight apart, then their speeds just add. So z prime has to be less than, well, 20 plus 10 or 30 kilometers an hour. Because we know they're not back to back. I mean, z prime is less than or equal to 30, but since we know they're not back to back, it's got to be strictly less than. So we want z prime in kilometers per hour, and z prime has to be between 0 and 30. I haven't done, you know, any like real math here. I mean, I guess I added 20 and 10, but I've just thought through the problem, right? I haven't done any real math, and I've got a lot of information about what my solution should look like. There's this guy, he's a professor at one of the big name institutions. I don't know, you know, Harvard or something like that, or MIT. And he actually wrote a book. I think it was called like Street Math or something, but and maybe like taught a course in it or like a little seminar in it or something, but it's just a bunch of tricks that are like this. You know, things like, okay, you have this problem, you work through it, you get an answer, you know, aside from just, you know, counting on the fact that the operations you did or you think are right, you really have no idea whether the answer is right or not. You know, what are some ways you can check your answer? In algebra, I mean, it's pretty easy. You plug your answer back into the equation and you see if it simplifies out the right way. But when we have, you know, more challenging questions like these, you know, once you get to calculus, it's a lot harder to actually check your answer. Um, So it's, you know, his street math idea is basically all of these kinds of back of the envelope type calculations or ideas that you can apply, things like checking units and so on, establishing what I like to call reasonability conditions. Like, does it mesh with your gut feeling? How should this work? Um, If we have a lot of experience with how things in the real world work, and if we think carefully about this, how should it work? Well, we see that z prime has to be in kilometers an hour, and it's got to be a number between 0 and 30. That gives us two pretty good conditions to check against later on. I know I've like beat this horse to death, but I think this is such an important part of the problem solving process. And it's so easy to just jump into it and try to get to the calculus right away. Okay, so now let's try to move on and relate the variables algebraically. So we want z prime, and we have information about x prime and y prime, and we can easily get x and y and probably z from just basic algebra and geometry. So I want to relate z, x, and y. That's my next goal. No calculus yet. We're not differentiating anything yet. We're not plugging in any numbers from up here yet. I mean, we plugged in the 90, but that's just because that's not changing. But x, y, and z are all changing over time. We got to be careful here as well. I mean, z is a hypotenuse. We have a right triangle here. The width of the right triangle, the like base of it, is 90. That's our east-west direction, that the boats are 90 kilometers apart east-west. And north-south, well, their distance apart north-south is actually x plus y. Well, Pythagorean identity is going to be really nice here. Z squared, hypotenuse squared, is the one side squared. Be careful here, that's x plus y all squared, which is not the same as x squared plus y squared. Right? We'd be missing a 2xy there. Plus 90 squared. I've now related my underlying variables. I related x, y, and z, the variables themselves. Now I can move on to differentiating. Again, I don't plug in 20 and 10 or any of that yet. So now I want to differentiate. Z, x, and y are all functions of t. So I take d by dt of both sides. And here's where I want to be good at the chain rule and implicit differentiation. The left side is 2z, z prime. Z prime means dz dt. Right? This is d by dt of z squared, which is d by dz of z squared times dz dt. There's dz dt. And d by dz of z squared is 2z. On the right side, I have 2 times x plus y to the first. Let me not write the first there because that looks like a prime. Times x prime plus y prime. And of course, d by dt of 90 squared is just 0. That's just a constant. I can solve for z prime. And I think this is what z prime should be. I don't really have a good idea of what size it is at this point, but I can check the units. If I look at this first factor, x plus y over z, x and y are in kilometers, z is in kilometers. Those units divide out. This first factor is unitless. My second factor, I have 2 terms, both of which have units of kilometers per hour, x prime and y prime. So z prime has units of kilometers per hour. So my units make sense. That's a good indication that I've at least gone the right direction. Okay, and now I want to go back, plug in constants, get my answer, and then check that it satisfies those reasonability conditions. Okay, well, I know what x prime and y prime are. I want to be careful with my signs here. Note that x prime and y prime, or x and y are both contributing positively to z. X and y are both distances. They're not sign distances. So just because ship A is traveling south doesn't mean that like x is going to be negative or the x prime is going to be negative. X just represents the distance between where ship A is at a certain time and where it started. That distance is a positive number, and the derivative of that is going to be a positive number as well. So x prime is going to be 20, right? Yeah, the one traveling south is 20 kilometers an hour. So x prime is 20, y prime is 10. I need to know x and y as well. These should be in kilometers. I'm not given x and y directly, but I am asked at 4 p.m. the same day when we started at noon, so 4 hours later, that's when I'm asked the information about z. Well, I know that 4 hours later, ship A has traveled a total of 4 times 20 or 80 kilometers south, ship B 40 kilometers north. So um, X is 4 times 20 or 80 kilometers, and Y is 40 kilometers. So that's not too bad. We also need Z. Well, I could get Z from here. Z squared is X plus Y squared plus 90 squared. Or I see I have a triangle that is 90, right triangle, that is 90 for one side. 80 plus 40 is 120 for the other side. Well, this is a 3, 4 scaled by a factor of 30. So I have a 3, 4, 5 triangle scaled by a factor of 30. 5 times 30 is 150. I could recognize the 3, 4, 5 triangle, or I could go through and algebraically solve for z using this equation. Either way. But I see that z has to be 150 kilometers. Notice that we've done a lot of work here, but we've kind of only done like, one real calculus step. I mean, I guess we need to know that x prime and y prime are these things, but there's really only like one big calculus step. And a lot of these applied problems, like this kind of related rates problem and things like optimization problems, there's a lot of setup that doesn't use calculus. There's like one calc step that's crucial, but just one of them. And then there's a lot of cleanup at the end. So like we did our big calculus step here, right? We couldn't solve this problem without this step. But I mean, we had to do a lot of work to get to that point, and we're doing a lot of work after that point as well. So what is my answer then? Z prime is, now I plug in all my constants, x plus y, 80 plus 40 over z, 150, times x prime plus y prime, 20 plus 10. We know the units are going to all work out right, so I'm not going to worry about the units. I'm not going to worry about tracking the units through. We checked those already. So this is 120 over 150, or that's what, 12 over 15, or 4/5. 4/5 of 30, or that is 24 kilometers per hour. We got an answer of 24. That does satisfy our second reasonability condition, being between 0 and 30. So I feel pretty confident that I've gotten the right answer here. Any questions on this problem? So there's kind of like two places we use calculus in here. One is taking the derivative, and the other is, I suppose, having to understand what we're looking for, what things, what things we want to end up with derivatives of so that we kind of have a strategy. But, you know, that's not really a direct application of the calculus properties that we've learned. We pretty much only have one step here where we did calculus, but it's quite a crucial step, right? We could not have solved this problem without this step. Okay, let's come down to this next problem. There are no questions. Here we have an example with 3 resistors. And suppose we're analyzing a circuit with 3 resistors connected in parallel. So I have a battery here, one resistor, 2 resistors. That's a wonky resistor there. 3 resistors. So I have 3 resistors in parallel. So I think of my, whatever way we want to think about it, I'm not going to, I think the short one is the positive and the long one is the negative usually. So I think of my electrons kind of, say, roughly speaking, coming out of one side and coming back to the other side. Let's just say they go this way. The electronics folks like to write the directional arrows one way, and the physics folks like to write it the opposite way because of electrons move one way, then negative charge moves that way. So which way is positive charge moving? But we're just going to write it whatever way. So my electrons want to go from one side of the battery to the other side of the battery. And the way I think about resistors in parallel like this is it's a little bit like if you have a bunch of people shopping and you have several checkout aisles. Like my electrons need to get from one side to the other. They're not all going to go through one checkout aisle because the other 2 checkout aisles have capacity and they're going to make use of that. Not everybody's going to line up at their, cashier number 1. So some electrons are going to go through this aisle, some through that aisle, some through that aisle, and they'll kind of come back together on the other side. Now, my resistors can have different resistances, just like cashiers. There can be the slow cashier. They don't allow a lot of throughput through their line. They get like, 2 people through per 10 minutes. And the fast cashier lets a lot of people through. So like the fast cashier is like a resistor with low resistance. It's letting a lot of electrons through it. So electrons will preferentially go through that resistor, but that doesn't mean that somebody is never going to go to the slow cashier. If there's 10 people in line for the fast cashier or nobody in line at the slow cashier, I'm going to the slow one. So resistors kind of like hold back electrical current, loosely speaking. Don't tell Professor Farina or any of your physics professors I'm talking about electrons like this. They'll, you know, I don't know, but these resistors resist the flow of electrical current. So that is what they do. The more resistive they are, the less, let's say something like the less likely an electron is going to go through that, the more impedance they have, or the more they get in the way of the electrical flow. So I have 3 resistors here, R1, R2, R3. They're connected in parallel like this, and the resistances are all increasing over time. So maybe we have a little knob that's attached to each of these essentially resistors, and we're just turning it over time and making them slightly more resistive over time. So R1 is increasing at a rate of 0.3, and this is like omegas per second. The omega symbol, or the symbol that looks like the omega symbol, is the ohm symbol. I think technically they're different symbols. Somebody said somewhere like, oh, well, the ohm symbol isn't the same as the omega. It's like, but it looks exactly the same. And I don't know why they have different, different characters for it, but I just used omega here. So resistor 1 is increasing at 0.3 ohms per second, resistor 2 at 0.25 ohms per second, resistor 3 increasing at 0.2 ohms per second. So they're all getting a little more resistive over time, but their rate of increase and the resistivity is going to be different between the 3 of them. The three resistors also have a different kind of starting resistivity. So resistor 1 starts at 50 ohms, resistor 2 at 100 ohms, and resistor 3 at 150 ohms. And our goal is to find the rate of change of the overall resistance. If I were to just kind of encapsulate this whole circuit and pretend like it was just one resistor, one big resistor R, or I suppose with multiple resistors, this would be a smaller resistor R, but one single resistor R that's handling all the current, right? So I have my three checkout lines. Some of my cashiers are faster or slower than others. They're all getting a little bit slower over time, providing more resistance to people checking out. But I could imagine that, you know, the process of just somebody checking out, I could replace those three cashiers with just one cashier who is checking out people at the same rate as the three combined. So that's what we're kind of saying here. What's the overall resistance of the circuit, and how is that changing over time? What is the rate of change of the total resistance when we're kind of at this snapshot in this movie as we're adjusting these resistances? And here, because this is a physics concept, I've given you the relation between the different resistances. So we actually start off right away having our algebraic relationship between all of our variables. But let's not jump ahead. Let's not get ahead of ourselves. So I note that all of the resistances are increasing. Now, if I had, one resistance increasing and two of them decreasing, there's kind of like countervailing forces there. I don't know who wins out. But if they're all increasing, I know that dr dt, the overall resistance, should be increasing. I also know that R, the resistance, should be in units of ohms. Sometimes if you see square brackets around a variable like that, that means units of. So the units of the resistance, the overall resistance, should be ohms. That's kind of like implicitly taken care of by the fact that this is the right physics equation to use here. So, I mean, that works out in this scenario. We didn't have to make the algebraic equation, so we don't have to really check that. But we also know that the units of dr dt should be like the units of these, like dr1 dt and so on. It should be ohms per second. We probably should check that. When we take the derivative, we should look through and we should make sure that all of our, when we simplify everything down after taking the derivative, that we do get ohms per second. Okay. So I would say at this point, step 0 is done. So moving on to step 1, well, step 1 is also done. We got that for free. Right. We're looking for the rate of change of R. We're looking for dr dt. And of course, the component rates that we have are the dr1 dt, dr2 dt, and dr3 dt. Those are related. Those are related by this equation. Or I might even write this as just r to the minus 1 equals r1 to the minus 1 plus r2 to the minus 1 plus r3 to the minus 1. I don't think I need parentheses on those, but if you want parentheses on them to keep the subscript and the superscript kind of, separated and looking a little nicer, no problem putting them in or not leaving, or putting them in or leaving them out. But there's my algebraic relation between the underlying variables whose rates I want to relate. Now I do my calculus step. Again, I don't plug anything in. I don't plug numbers in, because if I plug numbers in, then ddt, well, then all the number stuff just kind of, differentiates to 0. So I differentiate first. Remember, these R1, R2, and R3, these resistances are functions of time. So R is also a function of time. Everything in here is a function of time. So I have negative r to the negative 2 times r prime. Let me actually write that as dr dt. I know it's a little longer to write out, but since we already have exponents floating around, I don't want that prime to look like a 1. That's one of those bookkeeping things, right? Is like, I know that if I have a prime and it kind of looks like a 1, I might make a goofy algebra mistake. So I'll choose to write r prime this way instead, just so that that prime doesn't look like a 1. And I do the same thing over here, negative r1 to the negative 2. So I'm just bringing down the power, subtracting 1 off the power, making sure to go the right direction. Negative 1 minus 1 is negative 2 times dr1 dt. And then I have minus r2 to the negative 2 dr2 dt, and then minus r3 to the negative 2 dr3 dt. I mean, it's a lot to write out, but that's what it is. I can get rid of all my minuses, and I can multiply through maybe by an r squared. So all my minuses go away. I end up with r over r1 squared. And now I will switch to primes, r1 prime, because things are a little simpler now, plus r over r2 squared, r2 prime, plus r over r3 squared, r3 prime. I note that my rates are related. I have r prime related to r1 prime, r2 prime, and r3 prime. They all this relationship is also implicitly dependent on time through the presence of r, r1, r2, and r3, which are changing over time. They start out at these numbers, but over time they are changing. Do I get the right units here? Well, r and r1 have the same unit. Same with the second and third term here. So r over r1 all squared is unitless. I get ohms over ohms, that divides out. I square a unitless quantity, unitless. R1 prime is ohms per second. All of my terms on the right have ohms per second. On the left, I would expect ohms per second for dr dt. That was exactly what I was looking for. So my units come out right, even after taking the derivative and doing all of this bunch of algebra and all of that. I still have my units right, so I feel fairly confident that I did things correctly here. And only now that I have my rates related in kind of the abstract in the variable form, now I go through and I plug in all my values. So here's the R1 value, the R1 prime value. What is it? 50 and 0.3. I'm not going to carry my units through now. I already checked that the units mesh and they are what I expect them to be, so I'm going to leave the units off. R2 is 100. R3 was 150. R2 prime, I think, was 0.25 and 0.2, right? Yeah, 0.25 and 0.2. Again, I know that all the units work out, so I'm not going to track them through at this point. So r prime dr dt is what? Well, I need r over r1, r over r2, and so on. So I need to know r as well. So what is r? Maybe I'll actually do this in a different color because I'm kind of coming off to the side to do this. Well, I just go back to my algebraic relation. 1 over r is 1 over r1 plus 1 over r2 plus 1 over r3. So, oh, what did I do there? Hit the wrong button. Okay. Sorry about that. I hit function instead of control and it did something crazy. So 1 over r is 1 over R1, well, that's 1 over 50, plus 1 over R2, 1 over 100, plus 1 over R3, 1 over 150. Or I can put these all over 300, 6 over 300, plus 3 over 300, plus 2. It's 11 over 300 if I did my arithmetic correctly. Does that look right? Yeah, looks good. So R then is 300 over 11 ohms. Or say something roughly in the ballpark of 30 ohms. Does that make sense with everything in this context? I have basically one cashier who, let's see, higher ohms means more resistance, so they're slower. So one cashier, the 50 ohms is like the fastest cashier. So if I shut down the other two lanes, I would get a 50 ohm circuit. But if I open up more lanes, even if they're slower cashiers, the throughput is going to increase, right? So even if I have my fastest cashier by themselves, and then I open up another lane and their slower cashier that gets added, that still increases throughput. That still should decrease the overall resistivity. And this, R is say somewhere in the ballpark of 30-ish ohms. That's lower resistivity or more throughput than any of these individually. Okay, that meshes, right? That makes sense. So just because there's so much algebra and arithmetic and so many little details, I think just checking back in whenever you have an exam, whenever you have a chance to, something like this, does this make sense? If I made a mistake and I did R equals 1/50th and so on, I mean, a resistance of like 11 over 300, a resistance of, point, what would that be? 0.03 ohms or something. That doesn't really make sense. That's not even like on the same scale as these resistances. Or if I made another silly mistake and I ended up with a resistance that was 75 or something like that, right? If I just made an arithmetic mistake and got a resistance of 75 ohms, well, if I cut out resistors 2 and 3 and just made everything go through resistor 1, um, so I mean, I would get 50 ohms of resistance from just resistor 1. Then I add in more resistors and somehow my resistance goes up, even though I'm giving more paths, more throughput, that wouldn't make sense. So, everywhere I can, I try to check the reasonability of what I have at that point. Okay, so then R prime is going to be, now we're back to this equation up here. R prime, let me move this down a little bit just so it doesn't run into my R equals over there. And let me switch colors. There we go. R prime is going to be R over R1, or 300 over 11. And then over R1 is over 50 squared times R1 prime times 0.3 plus R over R2 squared times R2 prime and then plus R over R3. So 300 over 11 over 150 squared and times R3 prime 0.2. Now, a lot of the stuff in the parentheses simplifies out, like 300 over 50 is just 6, so the 6 over 11 squared times 0.3 and so on. When I did this, what did I get? I got about 0.11446. Those are fours, not nines. OneNote loves to try to help me with that. Ohms per second. So the overall resistance is increasing at about 0.1 ohms per second when each of the individual resistances is increasing at these rates and at the point in time when those three resistances are 50, 100, and 150 ohms. Any questions on that? Okay, now let's look at an example with two resistors. So this is going to be a slightly different goal for this example. So this is an example where we're trying to engineer into a circuit some stability with respect to temperature. So one thing about resistors is their job is to kind of hold back electrical energy in a sense. Um, but they do it by dissipating heat. They basically take that electrical energy that's trying to push those electrons through the circuit, say really fast. They take some of that energy, they dissipate it into the environment as heat, and that removes some of that energy so the electrons move more slowly. I mean, using pretty horrible analogies here, but roughly speaking, I think that gets the point across. If you want to see a really interesting video, look up Veritasium. His video on where he basically asked the question that like, if you had a wire that was like, I don't know, a light year long or something, you like wrap it around and you have a battery here, you have a light bulb that's like 1 foot away, but you have this huge long like line that goes way out that way and comes back to your light bulb. When you flick the switch, what's going to happen? Is it basically going to like, is the light bulb going to turn on basically right away? Is it going to take like, basically a year, like traveling at the speed of the electrical impulse, traveling at the speed of light down the line and back, taking a year to go along this light year length of wire, assume the wire has zero resistivity and so on. And really interesting. So he made this video and then several people made video responses to it and he made a video response to that. It was a really interesting dialogue, but in short, the way electricity works is really freaking wonky and crazy and unintuitive. But so we're using this model of like little doodads, floating around in these wires, but you know, there are a ton of caveats to that. Um, but if you're interested, look up that video, like probably something like Veritasium, you know, light bulb question or electrical circuit question or something will probably bring it up. Um, he's a good YouTuber in general. There's a lot of interesting stuff. But that was a really cool one. Okay, so let's consider this example where you have two resistors connected in parallel. So we have our kind of similar circuit as up above. And here we have two resistors that are made of different elements. They're made of different materials. One's made of iron, the other's made of silicon. So iron, of course, is a metal and silicon a semiconductor. Well, one thing about resistors is that their resistance tends to be dependent on their temperature, how hot they are at that point. If a resistor is in a warmer environment, it might get more resistive or less resistive. Its resistance might increase or decrease with respect to the temperature in the environment. So for each type of resistor, there is a number called the temperature coefficient of resistivity. For iron, that turns out to be positive. It's the number positive 5 times 10 to the negative 3 ohms per degree Celsius. And this is measured at 20 C, basically room temperature, 70-ish Fahrenheit. For silicon, it goes the other way. It's actually negative. Silicon resistors get less resistive when they're warmed up. Their temperature coefficient is negative 7.5 times 10 to the negative 2 ohms per degree Celsius. So let's suppose that we have some circuit on maybe an airplane or something like that, something that's going to be subject to extreme temperature swings. You're on the hot tarmac and it's, whatever, 110 Fahrenheit in like Phoenix or something. And then you fly up 35,000 feet and it's, I don't know, like negative 50 Fahrenheit or something. It's really cold up there. Um, so like, you have huge swings in temperature that these components have to deal with. And one way that you could try to engineer stability into the system is, maybe I could just make one resistor with like a little doodad over here that's like a heater and just, you know, just heat it up or air condition it and keep that, that board at that temperature. And but then kind of, if that heating element fails, then the board fails and or might fail. Can we engineer stability into the system? Can we replace one resistor with two resistors, but in such a way that they offset one another? So that as we increase temperature, one of them gets more resistive, one of them gets less resistive, and engineer it in such a way that the resistances just perfectly offset one another. We see we can't just use basically just two resistors of equal size or equal resistance because they have different temperature coefficients. The iron gets more resistive at a different rate than the silicon gets less resistive for a given, say, increase in temperature. So our goal is to find two resistors, the size of the resistances of these two resistors that we should use to make a total of 100 ohms of resistance. And so the dr by dt here, our independent variable is temperature, big T, is 0. So that if I'm sitting at 20C, I'm sitting at room temperature, and I wiggle the temperature a little bit, if I go up a couple of degrees or down a couple of degrees, my total resistance of my circuit will stay very near 100 ohms. So that's my goal. I know this wouldn't be something that you'd be expected to know for the course or on a test or anything like that. You'd always be given this equation if you needed it. But my resistor equation for resistors in parallel looks like this. 1 over R equals 1 over Ri plus 1 over Rs. As an aside, if they were in series, then they just add together. But if we just have resistors added together, that's kind of boring. It's just like one big resistor. So, right. From a math perspective, that's kind of a boring case. But that's like, you have a fast cashier and a slow cashier, but everybody has to check out with both of them. And well, everybody's going to get held up an equal amount. But this is for resistors in parallel like this, where roughly speaking, your electrons could choose which path they want to go along. Okay, we can actually simplify this right-hand side a little bit. I see this is going to have a denominator of Ri times Rs and a numerator of Rs plus Ri, or my overall resistance is just Ri times Rs over Ri plus Rs. So this formula works out pretty nicely in the case of just two resistors. Now my goal is to find Ri and Rs so that the total resistance is 100 ohms. And so the dr dt equals 0. So now I know what I need to do. I need to relate big R to big Ri and big Rs. I did that. And I need to differentiate that with respect to big T. So I now have step 1 completed. I guess we've kind of talked through the scenario, step 0 up here. Step 2, let me take d by d big T. And what does this tell me? Well, this tells me that big R prime equals, well, I'm going to choose to use this formulation because that's a lot easier to use than this crazy thing with like a quotient rule and a product rule and all that. So I actually jumped ahead a bit there. I'm going to use this formulation, which is attached to 1 over R. So I have R to the minus 1 equals R I to the minus 1 plus RS to the minus 1. To differentiate, I'll use this. To solve anything I need to solve with R and so on, I'll use the simpler formulation. But differentiating this would be a mess. So I get negative R to the negative 2 times R prime. And here R prime means dr by d big T, the rate of change of the resistance with respect to temperature, negative ri to the negative 2 ri prime minus ri to the negative 2 rs to the negative 2 rs prime. And same algebra as before, I'm going to multiply through by negative r squared. And that gives me r prime is r over ri squared, ri prime plus r over rs squared, rs prime. And now my goal here, as far as the derivative is concerned, is for this to be 0. So I'm going to set this equal to 0. Well, I guess I can divide through by an r squared. I guess I really didn't need to do that to multiply through by the r squared, but I think it makes it cleaner to do it this way. You can kind of see where everything's going. So divide through by the r squared, and I have ri prime over ri squared plus rs prime over rs squared equals 0. So I think as long as I divide it through by r squared, and I think I've distributed everything correctly, that looks good. So I have ri prime over ri squared equals negative rs prime over rs squared. I suppose I can maybe multiply my rs squared over and divide by ri prime. So I have rs over ri squared. That looks good. Equals negative rs prime over ri prime. So I have these relationship, or this relationship here, between ri, rs, and their derivatives.